Most people did well on question 3, which either means you've got a good understanding of this topic, or even if you haven't got a clue what's going on, you've learnt the rules and you've learnt the stuff and you're able to apply it. So, that squiggle's called sigma, so the sigma plus particle is a baryon with strangeness -1. How many quarks does it contain? Well, it's a baryon, so you can either remember the fact that baryons have 3 quarks. If you can't remember that and you're scratching around and you're looking at the data sheet, all the quarks there have got a baryon number of 1/3. And because it's a baryon, it's got to have a baryon number of 1, so how are you going to get a baryon number of 1 when you've got all the bits have got a baryon number of 1/3? You need 3 of them, don't you? So you need 3 quarks. How many of these quarks are strange? Well, if you've never heard of a sigma plus, again you might be reduced to looking at the data sheet. You look at the strangeness, you see that a strange quark has got a strangeness of -1. And the sigma plus has got a strangeness of -1. So how many strange quarks will you need to make that? Well, you just need 1 of them. Now, like me, you might be worrying that they've actually left you some space to do some working out here. And you might be thinking, well, perhaps you're supposed to do some working out. So just to be sure, let's see how I can make a sigma. It's got to have a strangeness of -1, so we know there's going to be a strange quark in it. It's got to finish up with a charge of +1. So we need 2 more quarks. So if we use a strange quark, the data sheet tells us that a strange quark has got a charge of -1/3. Got to put 2 more quarks in that are going to take us up to a charge of +1. So look at the table. No point going for another strange quark, because that's going to get us even more negative. No point going for down quarks, that's going to make us more negative. But if we have 2 up quarks, that's 2 lots of +2/3, which is +4/3. The -1/3 from that will give us a charge of +1. So that's what this sigma must consist of, a strange and 2 ups. But you got your marks just for putting that it was 3 quarks and that 1 of them was strange. Right, it tells you that the sigma plus decays in the following reaction, changes into a pi plus and a neutron. State 2 quantities that are conserved. Well, you've got a whole list of things to choose from. Charge is conserved, because there's +1 there, +1 and 0. Baryon number is conserved, because that's a baryon number of 1. That's baryon number of 0, that's a neutron, so that's baryon number of 1. The examiners let you say that lepton number was conserved. That's a bit of a cheat really, because lepton number is 0 and 0 and 0. So it is conserved. You're also allowed to say that mass is conserved or energy is conserved. And momentum will be conserved. So you've got lots of things there. You've got to choose 2 of them and get 2 marks. You don't get extra marks for putting extra things. State a quantity is not conserved in this reaction. Well, the sigma is a strange particle and the pion isn't a strange particle, so strangeness is not conserved. And in fact, strangeness is the only thing we've ever come across that isn't conserved. Conserved in some reactions and not in others. So if you ever ask for something that isn't conserved, then it will almost certainly be strangeness. What interaction is responsible for this reaction? Well, this whole reaction is about quarks changing into different sorts of quarks. And that's always done by the weak interaction. And into what particle will the neutron formed in this reaction eventually decay? Well, hopefully you know that there's only one stable baryon, and that's the proton, and every other baryon, including the neutron, will eventually decay into a proton.